Internet Protocol version 4 is the fourth version in the development of the Internet Protocol Internet, and routes most traffic on the Internet. However, a successor protocol, IPv6, has been defined and is in various stages of production deployment. IPv4 is described in IETF publication RFC 791, replacing an earlier definition. IPv4 is a connectionless protocol for use on packet-switched networks. It operates on a best-effort delivery model, in that it does not guarantee delivery, nor does it assure proper sequencing or avoidance of duplicate delivery. These aspects, including data integrity, are addressed by an upper-layer transport protocol, such as the Transmission Control Protocol. Addressing IPv4 uses 32-bit addresses, which limits the address space to 4,294,967,296 addresses. As addresses were assigned to users, the number of unassigned addresses decreased. IPv4 address exhaustion occurred on February 3, 2011, although it had been significantly delayed by address changes such as classful network design, classless inter-domain routing, and network address translation. This limitation of IPv4 stimulated the development of IPv6 in the 1990s, which has been in commercial deployment since 2006. IPv4 reserves special address blocks for private networks and multicast addresses. Address representations: IPv4 addresses may be written in any notation expressing a 32-bit integer value, but for human convenience, they are most often written in the dot decimal notation, which consists of 4 octets of the address expressed individually in decimal and separated by periods. The following table shows several representation formats. Mixing decimal, octal and hexadecimal is allowed in dotted format per octet. Note that in non-dotted formats, numbers bigger than 32-bit, can be given in some cases and will get converted mod 232. Allocation: originally, an IP address was divided into 2 parts. The network identifier was the most significant octet of the address, and the host identifier was the rest of the address. The latter was therefore also called the rest field. This enabled the creation of a maximum of 256 networks. This was quickly found to be inadequate. To overcome this limit, the high-order octet of the addresses was redefined to create a set of classes of networks, in a system which later became known as Classful Networking. The system defined 5 classes: Class A, B, C, D, and E. The classes A, B, and C had different bit lengths for the new network identification. The rest of an address was used as previously to identify a host within a network, which meant that each network class had a different capacity to address hosts. Class D was allocated for multicast addressing and Class E was reserved for future applications. Starting around 1985, methods were devised to subdivide IP networks. One method that has proved flexible is the use of the variable length subnet mask. Based on the IETF standard RFC 1517 published in 1993, this system of classes was officially replaced with classless inter-domain routing, and the class-based scheme was dubbed Classful. By contrast, CIDR was designed to permit repartitioning of any address space so that smaller or larger blocks of addresses could be allocated to users. The hierarchical structure created by CIDR is managed by the Internet Assigned Numbers Authority and the regional Internet registries. Each RIA maintains a publicly searchable WHOIS database that provides information about IP address assignments. Special use addresses. Private networks: of the approximately 4 billion addresses allowed in IPv4, 3 ranges of address are reserved for use in private networks. These ranges are not routable outside of private networks, and private machines cannot directly communicate with public networks. They can, however, do so through network address translation. The following are the 3 ranges reserved for private networks: virtual private networks. Packets with a private destination address are ignored by all public routers. 2 private networks cannot communicate via the public Internet, unless they use an IP tunnel or a virtual private network. When one private network wants to send a packet to another private network, The first private network encapsulates the packets in a protocol layer so that the packet can travel through the public network. Then the packet travels through the public network. When the packet reaches the other private network, its protocol layer is removed, and the packet travels to its destination. Optionally, encapsulated packets may be encrypted to secure the data while it travels over the public network. Link local addressing. RFC 6890 defines the special address block 169.254.0.0/16 for link local addressing. These addresses are only valid on links connected to a host. These addresses are not routable. Like private addresses, these addresses cannot be the source or destination of packets traversing the Internet. These addresses are primarily used for address auto-configuration when a host cannot obtain an IP address from a DHCP server or other internal configuration methods. When the address block was reserved, no standards existed for address auto-configuration. Microsoft created an implementation called Automatic Private IP Addressing, which was deployed on millions of machines and became a de facto standard. Many years later, in May 2005, the IETF defined a formal standard in RFC 3927, entitled Dynamic Configuration of IPv4 Link Local Addresses. Loopback. The Class A Network 127.0.0.0 is reserved for loopback. IP packets whose source addresses belong to this network should never appear outside a host. The modus operandi of this network expands upon that of a loopback interface. IP packets whose source and destination addresses belong to the network of the same loopback interface are returned to that interface. IP packets whose source and destination addresses belong to networks of different interfaces of the same host, one of them being a loopback interface, are forwarded regularly. Addresses ending in 0 or 255. Networks with subnet masks of at least 24 bits, that is Class C networks and Classful Networking, and networks with CIDR suffixes /24 to /32 may not have an address ending in 0 or 255. Classful addressing prescribed only 3 possible subnet masks, Class A, 255.0.0.0 or /8. Class B, 255.255.0.0 or /16. And Class C, 255.255.255.0 or /24. For example, in the subnet 192.168.5.0/255.255.255.0 the identifier 192.168.5.0 commonly is used to refer to the entire subnet. To avoid ambiguity in representation, the address ending in the octet 0 is reserved. A broadcast address is an address that allows information to be sent to all interfaces in a given subnet, rather than a specific machine. Generally, the broadcast address is found by obtaining the bit complement of the subnet mask and performing a bitewise OR operation with the network identifier. In other words, the broadcast address is the last address in the address range of the subnet. For example, the broadcast address for the network 192.168.5.0 is 192.168.5.255. For networks of size /24 or larger, the broadcast address always ends in 255. However, this does not mean that every address ending in 0 or 255 cannot be used as a host address. For example, in the /16 subnet 192.168.0.0/255.255.0.0, which is equivalent to the address range 192.168.0.0 192.168.255.255, the broadcast address is 192.168.255.255. One can use the following addresses for hosts, even though they end with 255, 192.168.1.255, 192.168.2.255, etc. Also, 192.168.0.0 is the network identifier and must not be assigned to an interface. The addresses 192.168.1.0, 192.168.2.0, etc., may be assigned, despite ending with 0. In the past, conflict between network addresses and broadcast addresses arose because some software used non-standard broadcast addresses with zeros instead of ones. In networks smaller than /24, broadcast addresses do not necessarily end with 255. For example, a CIDR subnet 203.0.113.16/28 has the broadcast address 203.0.113.31. Address resolution. Hosts on the Internet are usually known by names, for example, www.example.com, not primarily by their IP address, which is used for routing and network interface identification. The use of domain names requires translating, called resolving, them to addresses and vice versa. This is analogous to looking up a phone number in a phone book using the recipient's name. The translation between addresses and domain names is performed by the domain name system, a hierarchical, distributed naming system which allows for subdelegation of namespaces to other DNS servers. Address space exhaustion. Since the 1980s, it was apparent that the pool of available IPv4 addresses was being depleted at a rate that was not initially anticipated in the original design of the network address system. The threat of exhaustion was the motivation for remedial technologies, such as classful networks, classless inter-domain routing methods, and network address translation. Eventually, IPv6 was created, which has many more addresses available. Several market forces accelerated IPv4 address exhaustion: rapidly growing number of Internet users, always-on devices ADSL modems, cable modems, mobile devices laptop computers, PDAs, mobile phones. Some technologies mitigated IPv4 address exhaustion. Network address translation is a technology that allows a private network to use one public IP address. It permits private addresses in the private network. Use of private networks, dynamic host configuration protocol, name-based virtual hosting of websites, tighter control by regional Internet registries over the allocation of addresses to local Internet registries, network renumbering to reclaim large blocks of address space allocated in the early days of the Internet. The primary address pool of the Internet, maintained by IANA, was exhausted on February 3, 2011, when the last 5 blocks were allocated to the fiber IRs. APNIC was the first RIR to exhaust its regional pool on April 15, 2011, except for a small amount of address space reserved for the transition to IPv6, which will be allocated under a much more restricted policy. The accepted and standard long-term solution is to use Internet Protocol version 6. The address size was increased in IPv6 to 128 bits, providing a vastly increased address space that also allows improved route aggregation across the Internet and offers large subnetwork allocations of a minimum of 264 host addresses to end users. However, IPv4-only hosts cannot directly communicate with IPv6-only hosts, so IPv6 alone does not provide an immediate solution to the IPv4 exhaustion problem. Migration to IPv6 is in progress, but completion is expected to take considerable time. Packet structure: an IP packet consists of a header section and a data section. An IP packet has no data checksum or any other footer after the data section. Typically, the link layer encapsulates IP packets in frames with a CRC footer that detects most errors, and typically the end-to-end TCP layer checksum detects most other errors. Header: the IPv4 packet header consists of 14 fields, of which 13 are required. The 14th field is optional and aptly named options. The fields in the header are packed with the most significant byte first, and for the diagram and discussion, the most significant bits are considered to come first. The most significant bit is numbered 0, so the version field is actually found in the foremost significant bit of the first byte, for example. Version: The first header field in an IP packet is the 4-bit version field. For IPv4, this is a value of 4. Internet header length or, the second field is the Internet header length, which is the number of 32-bit words in the header. Since an IPv4 header may contain a variable number of options, this field specifies the size of the header. The minimum value for this field is 5, which is a length of 5A, 32 equals 160 bits equals 20 bytes. Being a 4-bit value, the maximum length is 15 words or 480 bits equals 60 bytes. Differentiated Services Code Point, originally defined as the type of service field, this field is now defined by RFC 2474 for differentiated services. New technologies are emerging that require real-time data streaming and therefore make use of the DSCP field. An example is Voice over IP, which is used for interactive data voice exchange. Explicit congestion notification, this field is defined in RFC 3168 and allows end-to-end notification of network congestion without dropping packets. ECN is an optional feature that is only used when both endpoints support it and are willing to use it. It is only effective when supported by the underlying network. Total length. This 16-bit field defines the entire packet size, including header and data, in bytes. The minimum length packet is 20 bytes and the maximum is 65,535 bytes. The maximum value of a 16-bit word. The largest datagram that any host is required to be able to reassemble is 576 bytes, but most modern hosts handle much larger packets. Sometimes subnetworks impose further restrictions on the packet size, in which case datagrams must be fragmented. Fragmentation is handled in either the host or router in IPv4. Identification Er, this field is an identification field and is primarily used for uniquely identifying the group of fragments of a single IP datagram. Some experimental work has suggested using the ID field for other purposes, such as for adding packet tracing information to help trace datagrams with spoofed source addresses, but RFC 6864 now prohibits any such use. Flags Er, a 3-bit field follows and is used to control or identify fragments. They are, bit 0, reserved. Must be 0. Bit 1, don't fragment, bit 2, more fragments. If the DF flag is set, and fragmentation is required to route the packet, then the packet is dropped. This can be used when sending packets to a host that does not have sufficient resources to handle fragmentation. It can also be used for path MTU discovery either automatically by the host IP software, or manually using diagnostic tools such as ping or traceroute. For unfragmented packets, the MF flag is cleared. For fragmented packets, all fragments except the last have the MF flag set. The last fragment is a non-zero fragment offset field, differentiating it from an unfragmented packet. Fragment offset, the fragment offset field, measured in units of 8-byte blocks, is 13 bits long and specifies the offset of a particular fragment relative to the beginning of the original unfragmented IP datagram. The first fragment has an offset of 0. This allows a maximum offset of 8 equals 65,528 bytes, which would exceed the maximum IP packet length of 65,535 bytes with the header length included. Time to live, an 8-bit time to live field helps prevent datagrams from persisting on an internet. This field limits a datagram's lifetime. It is specified in seconds, but time intervals less than 1 second are rounded up to 1. In practice, a field has become a hop counter euro. When the datagram arrives at a router, the router decrements the TTL field by 1. When the TTL field hits 0, the router discards the packet and typically sends an ICMP time exceeded message to the sender. The program traceroute uses these ICMP time exceeded messages to print the routers used by packets to go from the source to the destination. Protocol. This field defines the protocol used in the data portion of the IP datagram. The Internet Assigned Numbers Authority maintains a list of IP protocol numbers which was originally defined in RFC 790. Header checksum Er. the 16-bit checksum field is used for error checking of the header. When a packet arrives at a router, the router calculates the checksum of the header and compares it to the checksum field. If the values do not match, the router discards the packet. Errors in the data field must be handled by the encapsulated protocol. Both UDP and TCP have checksum fields. When a packet arrives at a router, the router decreases the TTL field. Consequently, the router must calculate a new checksum. RFC 1071 defines the checksum calculation. The checksum field is the 16-bit ones complement of the ones complement sum of all 16-bit words in the header. For purposes of computing the checksum, the value of the checksum field is 0. For example, consider hex 4500304422400080060008C7C19 ACI241E2B, using a machine which uses standard 2's complement arithmetic. Step 1, 4500 plus 0030 plus 4422 plus 4000 plus 8006 plus 0000 plus 8C7C plus 19 AC plus E24 plus 1 E2B equals 0002 BBCF. Step 2, 0002 plus BBCF equals 1 Barbadian dollar equals 101110111010001. Step 3, 1 Barbadian dollar equals 010001000101110 equals 442E. To validate a header's checksum, the same algorithm may be used. The checksum of a header which contains a correct checksum field is a word containing all zeros. 2 BBCF plus 442E equals 2 FFFD. 2 plus FFFD equals FFFF. The ones of FFFF equals 0. Source address. This field is the IPv4 address of the sender of the packet. Note that this address may be changed in transit by a network address translation device. Destination address. This field is the IPv4 address of the receiver of the packet. As with the source address, this may be changed in transit by a network address translation device. Options. The options field is not often used. Note that the value in the IHL field must include enough extra 32-bit words to hold all the options. The list of options may be terminated with an EOL option. This is only necessary if the end of the options would not otherwise coincide with the end of the header. The possible options that can be put in the header are as follows. Note: if the header length is greater than 5, that is it is from 6 to 15, it means that the options field is present and must be considered. Note: copied, option class, and option number are sometimes referred to as a single 8-bit field. The option type. The following two options are discouraged because they create security concerns: loose source and record route and strict source and record route. Many routers block packets containing these options. Data. The data portion of the packet is not included in the packet checksum. Its contents are interpreted based on the value of the protocol header field. Some of the common protocols for the data portion are listed below. See list of IP protocol numbers for a complete list. Fragmentation and reassembly. The Internet Protocol enables networks to communicate with one another. The design accommodates networks of diverse physical nature. It is independent of the underlying transmission technology used in the link layer. Networks with different hardware usually vary not only in transmission speed, but also in the maximum transmission unit. When one network wants to transmit datagrams to a network with a smaller MTU, it may fragment its datagrams. In IPv4, this function was placed at the Internet layer, and is performed in IPv4 routers, which thus only require this layer as the highest one implemented in their design. In contrast, IPv6, the next generation of the Internet Protocol, does not allow routers to perform fragmentation. Hosts must determine the path MTU before sending datagrams. Fragmentation. When a router receives a packet, it examines the destination address and determines the outgoing interface to use, and that interface is MTU. If the packet size is bigger than the MTU, and the do not fragment bit in the packet's header set to 0, the router may fragment the packet. The router divides the packet into segments. The max size of each segment is the MTU minus the IP header size. the router puts each segment into its own packet, each fragment packet having following changes. The total length field is the segment size. The more fragments flag is set for all segments except the last one, which is set to 0. The fragment offset field is set, based on the offset of the segment in the original data payload. This is measured in units of 8-byte blocks. The header checksum field is recomputed. For example, for an MTU of 1,500 bytes and a header size of 20 bytes, the fragment offsets would be multiples of /8 equals 185. These multiples are 0, 185, 370, 555, 740. It is possible for a packet to be fragmented at one router, and for the fragments to be fragmented at another router. For example, consider a packet with a data size of 4,500 bytes, no options, and a header size of 20 bytes. So the packet size is 4,520 bytes. Assume that the packet travels over a link with an MTU of 2,500 bytes. Then it will become two fragments. Note that the fragments preserve the data size, 2480 plus 2020 equals 4500. Note how we get the offsets from the data sizes, 0. 0 plus 2488 equals 310. Assume that these fragments reach a link with an MTU of 1,500 bytes. Each fragment will become two fragments. Note that the fragments preserve the data size, 1480 plus 1000 equals 2480, and 1480 plus 540 equals 2020. Note how we get the offsets from the data sizes, 0. 0 plus 1488 equals 185. 185 plus 1008 equals 310, 310 plus 1488 equals 495. We can use the last offset and last data size to calculate the total data size. 495 times 8 plus 540 equals 3960 plus 540 equals 4500. Reassembly. A receiver knows that a packet is a fragment if at least one of the following conditions is true. The more fragments flag is set. The fragment offset field is non-zero. The receiver identifies matching fragments using the identification field. The receiver will reassemble the data from fragments with the same identification field using both the fragment offset and the more fragments flag. When the receiver receives the last fragment, it can calculate the length of the original data payload by multiplying the last fragment's offset by 8. And adding the last fragment's data size. In the example above, this calculation was 495 times 8 plus 540 equals 4500 bytes. When the receiver has all the fragments, it can put them in the correct order, by using their offsets. It can then pass their data up the stack for further processing. Assistive protocols. The Internet Protocol is the protocol that defines and enables internetworking at the Internet layer and thus forms the Internet. It uses a logical addressing system. IP addresses are not tied in any permanent manner to hardware identifications and, indeed, a network interface can have multiple IP addresses. Hosts and routers need additional mechanisms to identify the relationship between device interfaces and IP addresses, in order to properly deliver an IP packet to the destination host on a link. The Address Resolution Protocol performs this IP address to hardware address translation for IPv4. In addition, the reverse correlation is often necessary. For example, when an IP host is booted or connected to a network, it needs to determine its IP address, unless an address is pre-configured by an administrator. Protocols for such inverse correlations exist in the Internet Protocol Suite. Currently used methods are Dynamic Host Configuration Protocol, Bootstrap Protocol and, infrequently, Reverse ARP. See also, Classful Network, Classless Inter-Domain Routing, Internet Assigned Numbers Authority, Legacy Internet, IPv6, List of assigned /8 IPv4 address blocks, List of IP protocol numbers, Regional Internet Registry, Notes, as an April Fool's joke, proposed for use in RFC 3514 as the evil bit. References. External links, RFC 791 a Euro Internet Protocol, http www.iana.org Internet Assigned Numbers Authority, http www.networksourcery.com Protocol Ipv4 IP Header Breakdown, including specific options, RFC 3344 IPv4 Mobility, IPv6 versus carrier grade NAT squeezing more out of IPv4, Address Exhaustion, RIPE Report on Address Consumption as of October 2003, Official Current State of IPv4/8 Allocations, as maintained by IANA, Dynamically Generated Graphs of IPv4 Address Consumption with Predictions of Exhaustion Dates Jeff Houston, IP. Addressing in China and the Myth of Address Shortage, Countdown of Remaining IPv4 Available Addresses, Further Reading.